Here's solutions to some more of the exercises from the inverse function theorem videos. The first ones that I want to do are some examples. So first, let's look at an example. It's trying to come up with an example of a continuous function that's not locally Lipschitz. Not too hard, because the intuition for locally Lipschitz just means that the slopes are locally bounded. The secant slopes are locally bounded. So we just need something that where the slope goes unbounded and yet it's continuous. The most standard example of that would be f of x is the cube root of x. There's the graph. And the tangent slope is unbounded. And it's not too hard to show that the secant slope is unbounded. Just fix one point at 0. F of x minus f of 0 over x minus 0. That's cube root of x over x. That's x to the minus 2/3. And that certainly goes to infinity as x goes to 0. So if you look at these secant slopes, they go to infinity. If we want something in 2 dimensions, I was trying to think if there's anything we needed to focus on that's really subtle or different in 2 or more dimensions, but not so much. So you could just say like f of xy is the cube root of x. And then that just makes this, just gives you kind of well, it's kind of hard to draw, but something that has that same shape in one direction and then is constant in the other direction. So next thing, let's look at an example of f that is locally Lipschitz, but not globally Lipschitz, just plain old Lipschitz. Okay, so here in any neighborhood the slope is bounded, but there's no global uniform bound on that. So notice this is not locally Lipschitz at this point. Oh, one other comment about this guy. To be a little more subtle, I don't think we really need to go into it, but this is only not locally Lipschitz at one point. And a question is, how many points could it not be locally Lipschitz at? Maybe there's some theorem that says if it's continuous, then maybe mostly it has to be locally Lipschitz. Well, there's this classic example, much more sophisticated than this, of the continuous but nowhere differentiable function, or a continuous but nowhere differentiable function, which hopefully, if you're in a sort of advanced calculus setting, you hopefully would have seen. And it turns out that if you work a little harder, that's not locally Lipschitz anywhere. That gets, at smaller and smaller scales, that gets jaggier and jaggier and jaggier. The slopes get steeper and steeper, and so it's nasty. And so that's nowhere locally Lipschitz. Really bad. Okay, or really interesting. It depends on your perspective. Really fractal is really a good way to say it, non-judgmentally. So how about locally Lipschitz but not Lipschitz? So that means that the slopes get bigger and bigger, but only as you like walk off to infinity. And this is a great example of a function that is really, I don't think anybody would say this is a pathological function or badly behaved, but the slopes get bigger and bigger as you go out. And so this is a big reason why it's really about locally Lipschitz a lot of the time. The global condition is just, we don't want to exclude that. It's a wonderful function. It's too strong. How about Lipschitz, but not differentiable? I gave a big hint. Easiest example here is y equals absolute value of x. That is the first function you almost certainly ever were presented with that is not differentiable. And that guy, but if you look at the secant slopes, they're either -1 if you're both on this branch, or 1 over here, or something less than, something between -1 and 1 if you cross branches. Pretty easy to show that those secant slopes are all uniformly bounded. So it's Lipschitz, not just locally Lipschitz, it's Lipschitz. Now, this is an interesting one. If you go more subtly, could we have something that's Lipschitz but nowhere differentiable? And in fact, this relates to what I was just talking about. There is a big theorem that says that Lipschitz implies differentiable almost everywhere. And that's a technical, it means except for a set of measure 0. And that may or may not be something you're familiar with. I'm not going to go into it right now. But it means roughly what it says. It's differentiable almost everywhere. That's it's a somewhat hard theorem to prove, I think. I can't remember the proof. So, and then, oh yeah, and then those were the main things I was asking in that exercise. Um, but I did mention if you want to think about uniform continuity, it doesn't come in too much. This is also uniformly continuous. That's actually, it's a bit harder to prove that this is uniformly continuous, not just continuous. But the easiest way is if you have the theorem that says if you have a continuous function and its domain is a compact set, like -1 to 1, then it's automatically uniformly continuous on that region. Okay, so it's you. This is a little bit. It's a good one to think about for uniform continuity. That it really is actually uniformly continuous here, but it's not locally Lipschitz. Okay, so the next exercise. Let's see. Yeah. So some more examples. Actually, let me do it in another video because it was really a separate exercise. So we'll do that in one separate video.